Okay, so this is our second type of transformation. These are called translations. Also, you've probably heard them called slides, right? So we have the translation, we have the idea of a slide. Okay, so the key to doing a translation is an idea in mathematics called a vector. Okay, a vector is usually drawn like an arrow, so it's going to look a little bit like a ray, but it has a definitive length. So if this is the vector v, its length matters. So the arrow point on a vector doesn't give that it goes on and on forever, but it gives its direction. Okay, so a vector is a mathematical entity or quantity that gives two things. It gives a distance, sometimes called a magnitude, and a direction. So this arrow has a fixed distance, which is its length or magnitude, and the arrowhead itself shows you what direction it's going in. So this could be called the vector v. Okay, so another way that we can represent vectors is using what's called rectangular component form. And in this form, we can write it, let's say I have a vector A as two components, with like an x component and a y component. Okay, x represents how far we are going to the right, y represents how far we are going up. So the how far is the distance to the right and up gives me a direction. So this is definitely a way to represent a vector. So let's, for example, take the vector 3, 4. This vector says start somewhere, go to the right 3 spaces, and up 4 spaces. So if I was to draw that vector, it would look like this. It has gone to the right 3 spaces and up 4 spaces. I clearly know the length or distance that I've traveled, and I know the direction that I've traveled in. So if this is the vector b in rectangular component form, in a drawing, it would look like that. Okay, so all of this has something to do with translations. So once I have the vector, I can describe a translation. Okay, so a translation is a transformation so we're moving a set of points using a one-to-one mapping, right? It is a transformation where all points in a figure are moved in the same direction for the same distance. Okay, so let's say I have a triangle. A, B, C. And I move A to here. So we're going to call that A prime. I'm going to move B to here. We'll call that B prime. And I'm going to move C to here. And we'll call that C prime. And I'll fill in the rest of the points. And now I have moved the triangle ABC all the same direction and the same distance and made the triangle A prime, B prime, C prime. Okay, so what you're seeing here is you're seeing a transformation, right? It's moved everything from one place to another. Now, here's the note. That motion, that motion, and that motion all have the same motion. And they all are moving along the same vector. They've moved the same distance, and they've moved in the same direction. Aha! So there's a connection here between this idea of a vector and the idea of a translation. And in fact, we typically describe a translation using a vector. So let's go ahead and do that. I'm going to make another triangle. Let's call it PRS. And I want to translate that by a vector V, which is going to say 4, -2. Okay, so this vector says go to the right 4 and down 2. So if I just drew that vector, I go to the right 1, 2, 3, 4, down 2. This vector V looks like this. Now note, a vector has no actual firm starting position. It can start anywhere. It can go, but it always goes 4 to the right and down 2. So if I start that vector at P, right? So I've got that vector V going that way. There it is. I have the same vector coming off S. There it is. And that same vector now coming off R. Right? So there it is. So here is where P is going to go according to this. There's P prime. There is S hanging out over there, so we'll call that S prime. S prime. And at the end of this is R, so we'll call that R prime. So let's make that a little bit different color so we can see it. Connecting P to R, connecting R to S, connecting P prime to S prime. So this over here is the pre-image. Down here is the image, and this is the vector that we have translated over. So if I translate the triangle PRS over the vector V, that's giving me the triangle P prime, R prime, S prime. Okay, so this is a translation given the vector, and it basically just tells me how to slide it. It says slide it to the right 4 and down 2. Slide it along this vector, which is what we did 3 times. 1, 2, 3. And this is our result. So let's note something here. If I take something, some object, let's say I have this quadrilateral A, B, C, D, and I slide it using some sort of translation into A prime, B prime, C prime, D prime, all the line segments stay the same size. So the object has moved, but the length of the line segments has not changed. So AB is the same length as A prime, B prime. BC is the same length as B prime, C prime. CD is the same length as C prime D prime. DA is the same length as D prime A prime. Since I have all the segments are maintaining their length, this means that a translation is an isometry, right? Because an isometry is a transformation that preserves segment lengths. And since we have that, all translations are isometries. Okay, so let's summarize. In order to do a translation, we have to move all the points a particular distance in a particular direction. Now, the mathematical tool that can do that very well is what's called a vector. Vectors can be drawn as directional arrows or can be written as a set of coordinates, right? These little bent brackets. Okay, so you move all the points according to this direction and distance, and you get a translation. When you make that shift from one place to another, you note that all of the side lengths are preserved. So all the lengths of segments stays the same, which means that a translation is an isometry. Alright, so there's our review. Thank you.